Great, thanks. Okay, let's start. So I will start with the exercises. Did anybody get a chance to do the exercises? Does anyone have any comment? Like, does anyone want to explain the solution? Like, the question was, what is wrong with this function? So yeah, so what I changed is like swap these two lines. So join used to happen before this line. Now it's happening after. So at this time, we're reading GCD result, but we haven't called join. So what happens is like this thread may not have finished writing its result to GCD. So the first problem is that the answer may just be wrong because the thread may not have just written it. So we may get some garbage here. So that's an issue. The other issue is like this program has undefined behavior and we will not be able to prove anything whatsoever. Like we can not even prove the most trivial spec for it. And if you know C++, like racing on this variable that is not atomic is undefined behavior. So this program is racing on this variable. Um, so if you look at the proof, what happens is when we do this division, just before we are doing this division, so this symbolic execution asks me some. So it asks me it's reading GCD results. So it's asking me any fraction ownership of of that location. And it says that prove me it has some value and you have any fractional ownership of it. But we don't have any ownership because we have given all the ownership to this thread because this thread is writing to it. So we have given all the ownership to that thread. So we don't have any ownership left to do the read. So that's why this proof doesn't go through. It breaks even before we have finished executing the program. So just before the division. Okay, so now let's get to the content today. So in the last lecture, we saw ownership of primitive locations, like things that fit in a word. We saw like integers and unsigned integers and pointers, memory locations. So now the first thing we'll see today is ownership of more complex data structures like arrays and structs and classes. And then we'll see how to do write, and rewrite concurrency. And then we'll end with a proof sketch of the execute block function. And a lot of what we are doing before like the execute block proof is to build up the concepts needed to understand that proof. So first thing we see is arrays. So that's the function. So let's take an example. This function is GCDL. So it takes an array of numbers and computes its GCD. And so here is the spec. As before, we say that this function has this argument nums, and that must be a location because it's a pointer. So what that argument gives you is a location. And then we're saying that at that location, we must have we have an array. And what that array is storing is this mathematical list of numbers. So this array R is a way uh, to say that at some location we have a list of items In this case, we have a list of numbers. And this argument says that how each of those items are laid out in memory. So each of them is a primitive. So just to give you an example, this is just saying that what does this mean? Like at some location P, we have an array of numbers n1, n2, n3. If we just unfold that definition, that expands to like at P, we have mn1, at P offset 1, we have n2, and at P offset 2, we have n3. It's like the usual meaning of arrays. And then there is this some C++ multiplier that we can ignore for now. Like the C++ has some rules. Like if you go more than one beyond the array size, it's undefined behavior. And to deal with those things, we have to track these things. Okay, so that was the argument, and it's a pre and post. So this function is reading the array. So so just a cube fraction is fine on each of those elements. And then the length argument must be an integer, and that should be equal to the length of this list. So it's equal to the length of the mathematical list. And the output is this thing called fold left. So Coq has this function fold left, which folds this operator on this list starting with 0. Just to give you an intuition of fold left of G dot GCD on n1, n2, n3 starting from 0 is like you first do 0 and n1, and then on the result you do GCD with n2 and n3. So that's fold left. It's defined in Coq. So this is the spec. Any questions?
So wait, why are you doing GCD of 0 and 1?
Sorry, can you repeat the question?
In fold left, like if we go back down, I guess like why is the inner GCD 0 and 1?
0 and 1?
Yeah. I guess like what does the 0 mean here?
0 is the initial argument of
Yeah, we start with 0. We can like start with n1 directly. That's also another way. It's just simpler, like for empty list, just returning 0. Just for less cases. Yeah. So in this case, what we can do, the next thing we want to say is like, so this is the spec.
Can I ask something?
Yes, please.
Who defines RAR? Which library defines RAR? Is it just like the primitive, or is it something that you constructed? Or
It's actually defined by the semantics, because when we initialize, so we have this function at the end that so like in this function test GCD, let's see, test GCD. This function like creates this GCD. So at the end of this command, we have ownership of the GCD. So the semantics uses this. The semantics uses it to define like what is the ownership after this has executed. So at that time we have an array. So it's defined by the semantics. But
semantics is given by the proprietary tool that converts C++ to Coq.
Yeah. So there are many ways to split it. Just like for primitives, we saw like we could split the fraction. Similarly, we can do this fraction split on arrays. So here it's saying that we have a q fraction on all the 6 elements, and we can split it into two ownerships, like 2 predicates, where we have q by 2 on all the elements, and we have another piece where we have q by 2 on all the elements. So what we can do is now 2 threads can read all. Now we can give this piece to one thread and this piece to another thread, and they both can read all the elements. Okay, so that was the picture, and this is a lemma which says that like q by 2 on all the elements. We can also do another partitioning, like if we have some program that like say increments all the numbers, has to increment all the numbers, then we can parallelize and we can give half of the we have one thread that's working on the left half, another thread working on the right half, and so we can split based on the cells. Like we can give ownership of different cells to different thread. So here we don't split the fraction, we split the different cells and give it to different thread. So I'll show you briefly an example of this kind of splitting. So this is this parallel GCD function. So what it does is it does the same thing. The spec is the same as this function, but it does it in a parallel way. It computes the GCD of, it splits the array into two pieces, and this thread, it forks a thread to compute the GCD of the left half, starts that thread, and then in parallel, it's computing the GCD of the right half, and then waiting, and then it computes, oh, sorry, I'm seeing the wrong function. This one is the same. So yeah, so in the right half, and then it computes the GCD of the both results after waiting for the previous thread to finish. Okay, so in this, so we can look at the proof just briefly. It has the same spec. And so if we look, so the new thing that we have to do here is we have this ownership, we had this ownership of the entire array, and we have now split it into two pieces. So at numsp, we have like just first n of length L by 2, and then we have split it, and then we have at the offset length L by 2, we have the remaining elements. So we split this ownership, and now just before starting the thread, we have to decide what ownership to give to that thread, and that the ownership that we give to the child thread is the ownership of the left half of the array, and the full ownership of the result L location, which it will write to. And then the only other thing that happens in this proof is that we have to show some equivalence. Like the spec is fold left of of all the operations like this. And what the code actually does is first folds left like this, then folds left on this, and then it does the GCD operation on both the items. So we have to prove that doing operations in this order is equivalent to doing operations in this order, where the operation being GCD. So that's a simple lemma we can prove by induction. So this is saying that we fold left for the first 10 elements, then we fold left on the last half elements, and then we do the GCD. That's the same as doing folding once. Okay, so that's what is happening. What the semantics computed is like, this is what the symbolic execution computed. And that's the post condition we need to show that they're equivalent, and that just using this lemma, we can do that. So now time for a quiz. We can generalize that parallel, these fold left functions. Instead of taking GCD, we can take a function pointer, and we can fold over an arbitrary function over integers. All I've done is just replace GCD by F and the 0 element by some ID element. And I've done the same to the parallel version, just replace GCD by F. So the question is, when are these two functions equivalent? When will they result? When will they return the same answer? What property do we need about F?
It needs to be associative, no?
Yeah, and what else? So in this, yeah, associativity is the main thing. So here I've proven the same lemma for an arbitrary function in Coq. For an arbitrary function Coq that takes two arguments and returns and thing, if the function is associative, and the ID is the left identity and also the right identity, then I can prove this generically in Coq. I seem to need this left identity and the right identity fact as well. I think we can do this, write this code a little differently in the case of the list having just one element. We can do special handling, and maybe we don't need the identity elements, but in this formulation, I did need the identity assumptions. And then what we can do is we can do the proof of this function generically. Like we can write the spec. So here is the spec of the generic parallel fold left. It says that add the function, add the argument f must be again a memory location called f pointer, function pointer, and at that memory location we have a function of that type and this spec. It says that it on inputs A, V, and BV, it returns FM of A, V, and BV, and FM we have quantified over, like for university quantified over some Coq function that represents that C++ function F. So, and then that function FM should be, F mathematical FM should be associative and left ID and right identity, and then we get this fact. So we can prove this generically. The exact same proof works. Okay, so the next thing I want to talk about is structs. So digging a little deeper into what we showed before. What we have this operation like double comma, that's the notation, and that is a notation of saying like if we have a memory location and then we have some offset, then this is the memory location saying that if we start from that location and take that offset, we get a new memory location. So that's this operator. And just before we saw, in the case of arrays, we already saw like one offset is like this array index. This is saying that of type 2 index 2, that's an offset. But we have other types of offset, like every struct field is an offset. So we can use that to define what does it mean to own a linked list node, which is right here, this definition. So it's saying like, what does it mean to like represent some mathematical data at a linked list node? We'll call node base as the base of that node. And that's where the node, that's the location of that node. And we're saying that at that node, we have the representation of like this data, this mathematical data, and this location for the next node. So if you unfold it, we're just saying that at node base, and if we start from node base and take the offset, this offset of the field, then we have the primitive. There we have the primitive representation of the data, and if we start from node base and take the offset of the next field, we have the representation of the memory location next look. And then this is just some boilerplate. It's like ownership of the paddings. The C++ structs can have paddings, and also this fact is like a standard thing. Like whenever we define the ownership of a struct, we add this fact. This also helps in type checking. Like this asserts that node base has the intrinsic type of that is node, and it helps in when we symbolically execute reinterpret cast and those things. This fact is used. So this is just a standard practice to add to every struct node. So now we can have the spec of very simple function. Increment data, so just increments data. And now we can use that node RF that we defined above. So it's saying that at the location n, the argument n, we have some location np, and the precondition says that at np we have the data and next location, and the postconditions that says that we have at np we have 1 plus data. The spec makes sense. So this node RF is just it's just a shorthand. Like instead of saying that, writing down explicitly like I have ownership of 3 fields, we can just write down in like more concise ways. Just a shorthand. Like it's nothing fancy going on here. And if we do the proof of this in data function, all we need to do is unfold. When we just unfold it, so now we get the ownership of the field data, full ownership, and now when we do the addition, Coq will happily do the addition, and the proof just goes through. There's nothing in this proof. Just once we unfold this definition, the proof is straightforward. So that was just that was for node. We'll see other examples where these things have more abstraction. Like here, there is no abstraction. Like in Cork also we have two things, and those are represented by the two fields in C++. We'll see other examples. Before that, I just want to say that this spec is not the idiomatic spec. The idiomatic spec is this one, where it looks more like the primitives. Like for primitives, like we have at the left of an arrow of this points to arrow, we had the memory location, and at the right we had a representation. So this is how we typically write, and so we can define this node R, the idiomatic one, to return a rep. And this rep is just the same type as that. Like morally is the same type, but it has some conveniences. Like you don't have to write down this base pointer all the time, and the star is also lifted to work on functions like this in the standard way. So there is nothing conceptually deep going on. It's just like a convenient notation to write these reps more easily. So that's the thing we'll use going forward. Okay, so now let's look at an example where we get some abstraction. So now once we have the node, we can do a linked list. So a linked list is just a pointer to a node. So we see what does it mean. So here we are defining what does it mean to how do we represent a mathematical list of numbers as a linked list in C++? How do we represent in memory? So here it's saying that if it's like a recursive definition, it's like a function definition, and it's saying that if it's matching on the cases of this Cork list, and it's saying that if it's nil, then the pointer should be a null pointer. And if it's some head and a tail, this is the tail of the list, then it says that then it says that the node must have the head value, and then this should be there exists some location for the tail, and the next field of that node should be that location, and then at that location we should have the rest of the list. So it's a recursive definition. Does that make sense? So just to give you an example, if we just unfold this definition, what do we get? So if we unfold that, we have at some head we have list R of Q of 4, 5, 6. If you just unfold the definitions, what we get is like at head we have the node 4 containing the node 5 location, and at node 5 location we have the node 5 and node 6 location. At node 6 location we have node R6 and null pointer. Just unfolding the definitions. And then we can write specs. So for example, spec of this reverse function in list is just at the argument L, we have some location LP, and at that location, we have a list R of L, some L called list L. And then the return value is some location R, such that at R, we have the representation of the reverse of the list. And we have full ownership because we are changing at least the next pointers. So it requires full ownership. So one question you can ask is why trust? There could be a bug in this definition in Cork. So this is a Cork function that reverses a list. There could be a bug in that. So we can look at the definition. It's like straightforward. If it's nil, then nil, and if it's head and tail, then you reverse the tail and then append X. So in this case, like it's already so simple that I tend to trust it. But other things you can do is like you can look at all the lemmas that are there in the library about it. There are a lot of things proven about it. So if any X is in the list, then it's in the reverse of list and so on. And then, for example, this lemma is interesting. Like it says that reverse of X append Y is the same as reverse of Y append reverse of X. Anyway, so that's I'll switch gears to concurrency. Any questions so far?
Actually, do you have this file somewhere available?
Yes. Let me post it. At GitHub, we should have crypto monad, and then if you go to the execute block proof branch, and then in this file, here if you go to demo2 proof.v, you should get this file. And the C++ file is in the same directory, it's demo.cpp. So I can maybe post this link on Slack. All right. Any other questions? Sorry, I should have done that before the talk. Okay, so move on to concurrency. So the last session, what we saw was when we the only concurrency we saw was that if a parent owns this thread, this ownership P, then it has just before creating a new thread, starting a new thread, it has to split its ownership into two pieces, and one piece, the other piece, it gives to the child, and the one piece, the other piece, it keeps for itself, and then when it calls join, it gets the child piece back. That was the only concurrency mechanism we saw last time. But that doesn't work for many cases. For example, let's consider this class, this simple function where we have an atomic U and we have this function set U. And we can have a very fine, like completely fine code pattern where the parent thread creates a child thread and both the threads are calling set U at the same time. And this will just not work in the previous paradigm because we are calling set, so we need full ownership, no fraction, and only one of the, and we have to decide whether we give to the child or not. Regardless, both are doing so, so there's no way to do the proof in the old paradigm. So we need something different, something new to cover these cases. So that's where it comes in. I think that's the main key concept like this is the heart of concurrency proofs, so-called concurrent invariants. And the idea is that informally, the idea is like we at any time we can take any resource and put it in a box. We call it a concurrent invariant. So we can take any resource and put it in a box. But the rules of the box are different. The rules of the box are like, you can put it in a box, but you can only open the box just before an atomic operation. So only when you're doing an atomic operation, you can open the box. And then at the end of the atomic operation, you must return the things to the box. So also a caveat, I'm only talking about sequential consistency right now. So these atomic operations, I'm assuming only sequential consistency, all these operations. So for weak memory ARM stuff, the rules are more complicated. But okay, for here.
Sorry, you said sequential consistency?
Yeah.
That is like strong consistency or?
Yeah, these atomics have this flag, like what is the memory order, and I'm assuming that all of these that argument is always the sexiest order. Yeah, so we'll say so now this works, right? Because the set U is an atomic operation. So just before set U, I get to open this invariant, I get this, I can use it and update the value, and this is existentially quantified, so I can change the value. Then when I go to put it back, it's existentially quantified, so I can pick the new value, 5. Then when I do set U6, again, I can open the box, get it, and change the value to 6 and put it back. So let's see how we do this formally in Quark. So we have this.
Sorry, one
Yes.
question. What's the difference here between existentially quantifying it and universally quantifying it? Like, why did we not say for all I?
Oh, this one?
Yeah.
This one would just be false, right? It says that it has all the values. So it says that it has 1 and it has 2 and it has 3. That's just wrong, right? It has at any given time it has one particular value, right? So it has to be existentially quantified. So
And so this is just indicating the value of the atomic variable.
Yeah, yeah. So this is an example. What we can do is, given formally, if we have any p empred, what we can do is we can put it in a box. So C is that box, is the concurrent invariant, and every invariant must have an ID. And we have fractional ownership of the invariant so that we can share the invariant across multiple threads. We can share the box across multiple threads. And then this P. This is saying that this box always contains P. And P can have complex logic in that, like if they have, it can have if then else, and we'll see today. And the thing is, the good thing is that once we have a C in QP, we can split it into Q by 2 or any other fraction. So now we can take an invariant. Once we have put it in a box, we can share that box to multiple threads. Even if that P itself is like the full ownership, in this case, this P actually is not splittable. Like it is complete full ownership of the location. So we cannot split P. Yet once we put P in a box, then we can split that box. We can make different pieces of that box and share with different threads. And all those threads can access the box and take out P just for one atomic operation, and they have to put it back.
And what if P had fractional ownership?
That's fine. We'll see an example.
So here P you have full ownership of P,
Yeah.
but if say you only had like read ownership of P, that's.
So we can define P as the fraction. We can choose P. So we can choose P to be the fractional ownership. That's fine. We'll see an example.
I see.
So we will
But
see
then
some.
you have to, I'm just wondering, what does it mean in the actual code? So you don't have full ownership of something, some P could be overwritten by some other thread.
Yeah, we will see some examples. So maybe like after 20 minutes, if it's still not clear, ask me again. Okay, so just just to get the rules clear, what it doesn't allow, let's take an example of just to illustrate what it doesn't allow you to do. So I have this bar function that changes Z, and I've written the spec where, like, in a box, I've put the full ownership of Z, and it has any value and full ownership of the pre-post. And that proof would not work. Why? Because when we do this, just for the write, Cork is asking me full ownership of that location Z, because we are doing a write. So the semantics is asking me full ownership. But what we have is that we have the full ownership, but it's in a box. And this is not an atomic operation, so we cannot open the box. So this is not provable. We
It's
cannot
not
open.
an atomic operation.
Z equals 1.
Z equals 1, like it's not, yeah. So yeah, Z is not an atomic field. So yeah, it's not an atomic operation, so we cannot open the box. So this is not provable. So now we take a different example where we can actually prove things. So we'll see proofs that go through. So let's take an example of this set U function. Actually, let's look at this function set then get U. So this is now we have U as an atomic, and then this function set then get U stores UV new. By the way, so this is a contrived example. This is the simplest I could come up with just to explain the mechanics. We'll see like more interesting examples, but just bear with me. It may seem a bit contrived, but just to get the mechanics of the rules clear, I had to pick the simplest example. So this is what it's doing is setting UV new to the location U, and then loading it and returning that value. So here is the spec of that function. So it says that in an invariant, I have some UV such that the global U has the value UV and the full ownership. And then it gets some argument UV new. So that's the argument integer. And say in the post condition, it returns UV new. So what is wrong in this spec? Like, we are getting an argument, we are storing it, and then we are loading it. And this spec says that we'll get exactly that value, whatever we stored. And this spec is wrong. And we will see why, where the cock proof fails. So we start the proof, and now we have the preconditions. So we have these preconditions. We have the full ownership of the location U in an invariant in the box. So we have just started the proof, and we are doing the store operation. That store operation. Okay. So now, just before the store operation, just like because the store operation is atomic, Coq opens the invariant for me. So what it has done is that the CN is gone, and we get it has unbared the invariant. The things inside it are now available for use, just because we are now doing an atomic operation. So now we can actually use this. So Coq gives me this ownership. And now I'm just calling it UV cur. So that existential, there was some value, so I name it UV cur. So that's just saying this is the current value of UV of U. And then it's we are doing a write. So Coq asked me for the full ownership of that location, and that's exactly what we have. So we instantiate X by UV cur. So now what we have is, now the write has just finished, and we have the post condition of the atomic write. Now it says that U has the value UV new. So the write has just finished, and we have the value UV new. And we have this modality here in the proof. This says that at this point we must close the invariant. So the semantics would prevent me from doing anything else. We have an open invariant, we have the atomic operation is finished, but until we close the invariant, we cannot do anything else. So it's tracking what invariants have been open, and one invariant has been open, so it is forcing me to close the invariants. So that's what we do. So now we are closing the invariant. So to close the invariant, whatever was the argument of that CINF, we have to give up exactly that. So it's asking me, give me these resources back. So fortunately, that's exactly we have in the context. So UV new, we can just instantiate UV by UV new, and we are done. We can instantiate that. The only thing is that we will lose that. Like it's like a wallet, and this is like a transaction, and it's asking for that token, and so we lose that token from the wallet. So that's the key part. So we lose that thing. So once we're done, we get back the scene. It's like a Uniswap, like that's the post condition of closing invariant. We get back the box, but we lost the thing. So now it only says that there exists a UV. U has some value UV. It doesn't say that it's UV new. It doesn't say that it's UV new. Once you have closed the invariant, it doesn't say that it's UV new. And it makes sense, right? Because at this point, any other thread can come in and change the value. So now we have lost the fact that it was UV new, and now we are back to like it's any UV new. So now when we are doing the load, we can again open the invariant. So we are doing the load and we open the invariant again, but this time we just get there exists some UV there, and there is no reason why that UV would be the same as UV new. So that's why this proof doesn't work. At the end, what we have is like the semantics returns UV, and the post condition asks me to that value is we are returning UV new, and there's no way to prove that they're equal. So that's the correct spec. It just says that you return any value. Okay, so this is not very like not very satisfying spec, like the post condition just says that you return anything. Just as morally, the post condition just says that this invariant will always be maintained. That we already know, like every invariant, you can think by induction, like every atomic operation reestablishes it, and non-atomic operations don't even touch it. So it always holds. Okay, so now we'll see some more. I'll make the spec a little more interesting. So what we can do now is write the same function, write a different spec, where the invariant says that the number is prime. So it says that there exists a UV, that we have UV, and UV is prime. And then we take a UV nu. We cannot prove this spec. And can somebody guess why we cannot prove this spec?
So that's for the same program, right? So in that case, it could be that there's another thread that's overwriting you in
Well,
between.
that part I fixed. It's returning any. So there is a missing precondition. A hint, there is a missing precondition. So we can look in the proof, and Cock will tell me what we're missing. So just the proof is just as before. We can open the invariant, we get some UV. I call that UV before the write, and after the write ends, we get that UV new. We know that UV before write, that was prime. And now the write has set the value to UV new. Now when we go to close the invariant, Cock is asking me to return back the contents of the invariants. And now we have to instantiate UV by UV new. That's the only choice, because that's the only ownership we have. But it will also ask me that UV new is prime, and we don't have that. The precondition didn't require that UV new was prime. So when we go to reestablish the invariant after the write, we fail. So the correct spec is that there should be a precondition that UV new is a prime, because we're changing the value to something new, and the invariant says that U only has prime numbers, so the new value must also be a prime number. And
We specify that only should be branch, like that's the
invariant, the invariant says that
that's the invariant for the atomic, like the box, or like where did we specify that the value should be branch, like in which invariant?
in this invariant, like here,
In the wrong spec. I think.
here, oh sorry, in this spec. Oh, you're talking in the wrong, in this spec? Yeah, so we are saying that we have established an invariant. So the ownership of U lives in a box, and that box has this invariant. So that's why we fail here, because we don't have that. Okay, so so in this spec we fix the precondition, and as a bonus we also get a post condition. Like again, we return anything, we don't know what it is, but we know that it is a prime, because the invariant says so. And this proof grows. The only interesting part in that proof is just to remind you that is prime is like a pure fact, like it's is prime of some Cock number. It says nothing about the memory. So, and those things are duplicable. So is prime I, we can duplicate into is prime I and is prime I. So what happens is when we open the invariant to do the load, and then when we close it, we can make a copy before closing the invariant, so that we can keep that copy to return as a post condition. That's the only difference in that proof. And that's why we can return that whatever this function returns, it will be a prime number. Okay, so that was to explain the mechanics. Now we'll get into more interesting examples. And just a overview. So in sequential proofs, proofs of sequential code, typically loop invariants are the most challenging thing. They're the constraints. And in concurrency proof, the analog is these concurrent invariants. So whenever we have to like do a concurrency proof of a complicated library, the most difficult part is like deciding what should be in that invariant. And it can be very complex. I've written invariants like with hundreds of lines of resource of assertions, and and lots of conditions, and then even why scene like is a little more difficult. Why? Because like in loop invariant, the only condition is that it should hold at the beginning of and end of the loop. And you only have to worry about that function. With concurrency invariants, like they should always hold. They have to be always preserved. And let's say like if you have a concurrent library that has like 6 methods, and so you have to keep tweaking that scene until the specs of all those methods can work. Like all those methods, you have to do this iteration, like keep tweaking the scene until the proofs of all those concurrent library methods work. So the invariant has not only the invariant has to be always hold, but also like the invariant should be strong enough so that the post conditions of those methods actually work out. So next we'll see a little. So we'll see a different example of an invariant. Here we have an if then else. That's a common pattern. So let's take another example. Like here we have a spin lock, very simple spin lock. We can take a, and then we have a list that we have protected by a lock. So this is a concurrent list, very simple. And the only thing is that, sorry, any questions? So we have a list, and this list is now protected by a lock. So when we do a push, we first take a lock and then do the push operation, and then we unlock and then return. Similarly, if you want to reverse the list, we first take a lock and unlock. So we can have this setup. We can have this setup where we have 2 threads and they both call push concurrently. And the lock would enforce an ordering that so that the pointers of the linked list don't go haywire. So the lock would enforce the ordering. So, but this represents a challenge that we haven't seen before. This push, this is changing pointers that are not atomic. So if we look at the definition of node, these pointers were like not atomic. This data was not atomic. So what this example shows is that somehow this thread must be able to take out ownership of non-atomic things. So at this point, this thread has the ownership of non-atomic things. And at this time, this thread has, the child thread has ownership of non-atomic things. So that's a new pattern that we haven't seen. We don't need any new primitive. Just using scene, we can establish that pattern. So for that, I'll just take a look, we'll take a look at this lock spec. And that's where it lets us take and receive other different threads taken out, take and put back ownership of non-atomic things. So we'll see the spec of this class briefly. So this very simple lock, it has an atomic called locked Boolean. And if we want to unlock, we just store false there. And if we want to lock, we try to store true there. And we only return, so if you haven't seen atomics, like what exchange does is it atomically reads the value of foo and sets it to bar. It's very important that both these steps are atomic. And then it returns the original value. So that's the key part. It returns the old value. So this loop would only terminate when this exchange atomically flips the locked from false to true. That's a very important point. That's how this definition of the invariant would work. So now we can see the definition of this lock representation predicate. So it says that it's parameterized by some lock protected resource. So it says that when you construct a spin lock, when you're doing a proof of the caller and it's constructing a spin lock, it gets to choose any lock protected resource. It gets to decide what resource is that lock protecting. Okay, and that lock would have an invariant which goes like this. There exists some locked, and at the field locked, at that field, we have that value locked, like cock value locked. And this is the interesting piece. It says that if locked, then there is no other thing. But if the locked is false, then this invariant has this lock protected resource. And this can have ownership of like non-atomic fields. It can have the ownership of the entire linked list. So the key part here is like when we flip from false to true, what happens is in the atomic operation where this lock flips it from false to true, what happens is when we do that atomic operation before in the pre-state, we must be in this case. So we know that the lock protected resource was in the invariant, right? Because it was false before. We know that it was false. Only then we return. And at the end, what happens is we are in this case. So when we go to close the invariant after writing true, we do not have to return back lock protected resource. And we get to keep it and return it as a post condition to lock. So that's why we see this lock spec. So the spec says that there is some lock R of lock protected resource, and the post condition returns back the lock protected resource.
Can I add something?
Sure.
Is this for an example, right? This is not how we actually do logs. Because
Yeah. This is a
it's
simplified
been-
example.
Right.
Yeah.
So you don't want to do it in seconds.
Yeah.
This is only returning the lock protected resource. This is one branch of the if condition, right?
Yeah, but we only return, we never return until this happens.
So did you have to write this spec or is this automatically generated for as
No.
part of the library? I think the semantics.
No, we have to write these specs. So yeah, I wrote this specs and there is a proof in this file. We won't go through, but hopefully the high level argument made sense. And conversely, like when the unlock has the opposite spec. In the precondition, we give up the lock protected resource and we don't get it back. And this lock R is a prepose, and lock R is fractional. So you can put the resource in the lock and then share that lock with many different threads. They can all try to do unlock. Okay, so that, and just an example for that concurrent list, we can define a predicate where we put the ownership of the entire list R, like at that base field, whatever, at that head field, the entire list ownership that lives inside a lock. So that's the lock protected resource when we define a concurrent list predicate. We put the ownership of the entire list in that lock. And then that's why when this lock returns, we have the full ownership of the list, so we can do whatever we want. Same here, and then when we call unlock, we give it back. Okay, so that was a detour. I want to get back to this example, to the same example of set get you. Just to explain one last thing before we look at block state specs and execute block proof. So there's one concept that I need to explain that. So in many applications, especially if you look at execute block, what happens is like there is one thread there's only one thread who can do the write, and all other threads can read. So if you know execution code, what happens in execute block is that at any given time, exactly one thread can be committing. And that thread is updating the state. And all the other threads can read, but they cannot write. They cannot update the state. So I just want to explain that pattern, how to achieve that pattern using the existing concepts. And so so I'm just trying to illustrate those with this example. So here we have to set up a protocol where exactly one thread gets to store, but concurrently all other threads can read. So to do that, we don't need any new concept. We can just use the old concept. The only thing different is like at this time in the invariant, we only put half ownership of U. We still say that it's prime, it's fine, but the only difference is we put only half of the ownership in U. And then we define this piece auth. So in the separation logic literature, there is this terminology called auth and fragment. So there is only this ownership auth. There's this auth ownership that has no fraction and has only one. So this is the ownership that the writer would have. So writer would have the invariant, and it will have the other half of that ownership of that location. Right, and the writer gets to say that the current value is UV because it has the other half and it can say that the current value is UV. And the other half lives in the invariant. And this U auth doesn't have a fraction. It doesn't make sense to split it because if we split the pieces, then we have half fraction in the invariant and 1/4 separately. So we only have 3/4. Even after opening the invariant, we'll only have 3/4. So we won't be able to do it right. So it doesn't make sense to split this. So U auth R cannot be split. It is only one. And then in contrast we have this U frag R, which just has ownership of the invariant. And this part we can split with as many readers. So this is the ownership which we give to the readers. So U frag can.
How do we say that only, like, we don't know in advance which thread will write, but only one of them can write. But this is saying that one of the threads already has ownership of like the remaining part.
Yeah.
So would we have to kind of existentially quantify like there exists one thread which has like the remaining ownership? Like how do we?
So we can
How
do
would we-
we can do that later. Like we don't need to talk about threads here. Like once we initialize, once we like we think of main gets ownership of the entire field and we store a prime number there. So we have this and now we create an invariant and put the stuff there. And now we get those two pieces. And now we can fork a thread and we just get to choose which thread to give U auth R. And those threads can pass. We'll see examples in the execute block. We'll do these things. So we can choose later to give.
One more quick question.
Yeah.
The earlier predicate that we saw in C++, like the exchange operator,
Yeah.
the semantics for exchange and like the specification for that was also kind of generated already, or that must already be like a definition defined already for
It's
analog
slightly,
corresponding to exchange.
yeah, so the atomic itself is a standard library function. It's not given by the C++ standard. So that is like a proven spec, but there is an underlying operation which has an atomic spec. So
The
it's,
exchange is the underlying.
yeah, it's morally defined. Yeah, it's morally defined by the semantics. Not quite true, but morally that's right.
And you only need an atomic, really need kind of the level of exchange for the class. That's why we were only working with like the specific.
Yeah, we only do that. So
I thought that what Kushal was saying was basically that I guess this is showing a special case to the more general thing. The more general thing I could prove is that anybody can acquire the right look and I don't have to choose which thread that is.
yeah. So
But here I think you choose who you give the auth to, right?
you can do that. You can put this auth R again in some kind of invariant, and
Yeah.
you can do that. Like you are free to choose the protocol. You get these pieces, then later on you can decide how you want to share these pieces. But the key thing is you have exactly one piece, unsplittable piece called U auth R that cannot be split, and you have this U frag R that can be split in however pieces you want. Okay, so now we see the spec of we see the spec of this function. Sorry, we see the spec of. So there is this get U, and now the spec of it becomes interesting. So get U has two specs. One is like if you have a frag R, if you only have the fragment, and notice the fragment doesn't say like what is the value because existentially quantifies it in the invariant. So if you have a frag R, then all you get is that it returns any value. All we know about it is that it's prime. In contrast, if we have the auth R, and then you do call, call get U, then you know that the answer would be exactly U val. So that's the authoritative says that it has authoritative knowledge of the current state. And the fragment means like it has fragmented knowledge. It doesn't have full knowledge of the current state. It just knows that it's prime. And then set them get U now has a more strong spec. It says that previously the U had some old value. We write it to some new value. That must be prime. It's a precondition. But at the end, we know that we still return the same value. And at the end, we know that it still has the value that we chose. And why this works is because we have the other piece that's needed to write. So we can establish this. So we can briefly look at the proof. So this is just the start. We have the we have one half that we own in a bare way, like privately, and the other half that is in the invariant. Right. So that's the starting state. And now we go to do the write. And for the write, we can open the invariant. And now we unbear the part in the invariant. So we have that part that we had privately, and that this part we get from the invariant. And now we use this lemma. This is the key lemma, which says that if you have an atomic at the same location, if you have an atomic with V1 and another piece that says it has value V2, and note that Q1, Q2 are like positive fractions. So like if we have some assertion saying that it's V1, another assertion saying that the same location has V2, then they must be equal. Because at that location, we have exactly one value. So it's not like a Heisenberg location. So V1 and V2 must be equal. And then we can combine the fractions. So we use this lemma now here to combine the fractions. So and what we also get is that we get that these two are equal. And we combine the fractions to get one. And that the right requires the one fraction. So we can combine those two pieces, and now we have the full piece needed to do the right. And now we do the right, and now we get the post condition of the right. It has the new value. Now we close the invariants. So when we close the invariant, it only needs half, and we have one. So when even after closing the invariant, we get to keep the half, the other half that says that it's still UV new. And the invariant says that it's existentially qualified, but we still know that it's UV new. So other code can still run here, but we know that code, intuitively we know that code cannot write it because we privately own that piece that needs to write, and no other thread is, so no other thread can write. Invariant only has half fraction, so no other thread can write. So even though other threads can read, they cannot write the values, so we can stick to, we can assume that it's still UV new. For the load, we again, the same thing happens. When we open the invariant, we get a UV at load, but because we have that piece, we can use the same lemma again to actually assert that they are the same. And now we can finish the proof. So we get that, we get back exactly what we stored in this case.
For proving the U dot load step, did we have to kind of use some lemmas around the fact that nobody else can have full ownership of this? Like we had the authoritative ownership, like the remaining part of this.
No, we don't. That was just an intuitive explanation. That's the beauty. Like you do not have to reason about what others own. What you own gives you like the right, tells you like what you can do. Like you don't have to worry about what others own.
Yes, I'm trying to see why is that intuition not needed to be proved? Like why did we not need to prove that intuition? Because how's the proof going through otherwise?
Okay. Let me try to explain it. So this is the step where we
Because
just
U dot load will just say that, if you'll just get any value, there exists any value.
yeah.
You'll have to say that because you own the remaining part, nobody else will have it. So
Yeah, this is exactly where the combine helps. So right, we at this point we have this is the piece that we had held privately. And this piece already said that the value is UV new. So this piece is saying that intuitively this piece is saying that the value is UV new because we have the combined lemma. So so we don't have to worry about what the other thread, and that was just to explain you, but you don't have to do that. Like because we have this assertion, we know that it's UV new.
So this is intuitively kind of like, so I mean, tactically speaking, it's basically saying that if anybody else needed to modify this value, they would have to open the invariant, right? And
they get only half.
Yes. But we already have the UV new value, so we don't even need to like. Yeah. Okay, makes sense.
Yeah, this is intuitively just says that this says that the value is UV new. So this assertion says exactly what we need, and that was just to explain that no other thread can do this. Okay, so That's all for now. We'll look at the actual execute specs. So now I just want to show you the specs of block state. So there's this block state, as I said, like it uses the same pattern. And so there is this function read storage that during execution, if you are emulating the sload operation, you can call this function and it will read the key. So this function also has two specs. One is where it only has the fragmented ownership. Like this is saying the fragmentary ownership of block state. This is useful in the speculative phase. It says that if you only have fragmented ownership, then you get any value. Like we don't know what we get. Like we get at the return value, we have something, we don't know what it is. It works for the proof. And then the other spec says that if we have the authoritative ownership, and that has some pre-TX state, then we know that it will return the actual value where we look up that key in the pre-transaction state. And similarly, we have this block merge, which requires the authoritative state. Like if you want to actually update the state, we must have the authoritative state. And then it changes the auth to apply the updates. So morally, the state type represents assumptions and updates, and it will update. It will change the auth to apply the updates. And there is a precondition says that the assumptions must be true about the pre-TX state. We can get back into this later, but I want to like now do an animation showing how this proof works and how the ownership flows in execute block.
We have to write the entire spec by ourselves.
Yeah.
Okay.
Okay, so this is the execute block function, and it's at the beginning we have like the auth of block state, and it says that it has some pre-block state, PBS, and it has the frag of 1. And suppose there are 3 transactions. So what we'll do is like we'll split the R frag 1 into 3 pieces and give the 1/3 to each transaction. Now all these transactions can start speculatively executing. And let's say at some point T2 finishes. So now T2 waits on some kind of a signal. And then let's say T1 finishes and it waits for some signal. So one thing is what happened before is like the main function, it calls some signal. It signaled after starting the threads, it would signal the first thread. And as a part of that, it gives up the ownership of RAuth PBS and it goes to some invariant, signal invariant. And then this T1.sig.wait immediately resumes. And as a post condition of that wait, it gets the ownership of RAuth. Just like in the lock, we took some resource out of the invariant in the lock function, just like that wait takes the ownership out of that invariant and it gets the RAuth of PBS. Now the first function calls merge. And while call this merge, T3 may still be doing racy reads while the merge is happening. And the result at the end, what happens is we get RAuth of T1 PBS. That we go from RAuth of PBS to RAuth of T1 PBS, which T1 PBS says that is the result of executing T1 on PBS according to the official EVM semantics, sequential EVM semantics. And then it does T2.sig. That waits that guy. And then as a post condition, it transfers that RAuth to the second thread. Okay, and now that second thread will check whether the assumptions made here was sound with respect to this state T1 PBS. If it's not sound, it will re-execute. If it's sound, it would directly call merge. Either way, it calls merge, and as a result of merge, now the RAuth is like T2, T1, PBS. Okay, and same thing, ultimately, it calls signal that wakes up the third thread. It gets RAuth of that, and then it calls merge. It becomes T3, and then it calls msig, like signal the main thread, and the main thread has, what happened? So the main thread, yeah, the main thread has a signal, waits on the last one. So now the main thread gets T1, T2, T3 of PBS, and that was the push condition of execute block that we saw last time. So we have shown the flow of block state RAuth and RFrag pictorially, and this is like this kind of paper proofs of how the ownership flows and assertions flow is useful. Often before doing cork proofs, I do them on paper, and many times like it can be a substitute. It can be a substitute for cork proofs. Like using these concepts, you can sketch out the proofs at this level without actually doing them in cork. With cork, you get some help. It checks if you made a mistake, but even this can be useful. Okay, so one last thing is like often this is actually a real story based on what happened. So often when you see the specs and you have too much ownership, you have unneeded resources. Often it means that your specs are your code is overly sequential. So what happens here is like here we have our auth, like this thread gets RAuth of like the entire thing. But let's say this T2 transaction is only writing to one account. It doesn't need the ownership of all the accounts. Yet we have the ownership of all the accounts here. So we have more ownership than we actually need. And that often means that we may be missing out on some parallelization. So that's what we did while writing the specs, I noticed that this has more ownership, and I thought maybe there's missing opportunities for parallelization, and that's how I came up with this parallel commits. So that's the last thing we'll see today. So we'll see how parallel commits work. I haven't done the proof, so it's just a paper sketch at this time. But this is more interesting. So in parallel commits, what we do, we split the frag like this before. So let's back up a little bit. We have three transactions, TA, TB, TC. I just renamed from T1, T2, T3. And we have just two accounts. Let's assume for simplification, the entire EVM universe has just two accounts, AC1 and AC2. And we are showing that TA just writes to AC1 and TB writes to AC2 and TC writes to AC2, only to AC2, writes or reads to AC2. So I've written the footprint, like TA only reads, writes to accesses, changes AC1, TB and TC only read, write AC2. Okay, so now what we can do is we can split the frag just like before, but this time we can also split the auth into two pieces. This is saying that the auth of the first account, this is now just saying asserting authoritative ownership of just the account AC1. This is saying that authoritatively that the state of the first account is the same as what it was in the pre-block state. Same as the state of the first account in the pre-block state, and this is saying that the state of the second account, AC2, is the same as the pre-block state of the second account. So we have split the authoritative into granular level, one for each account. And it's all happening in the logic, like we don't need to change, but in the logic, we can split this further. And now what happens is
One quick question.
Yes.
R flag, did you not need to split R flag as well? Because
Yeah.
while I'm writing to account two, I can read account one easily. I should be able to read account one easily.
Yeah, but rflag doesn't say anything about the current state anyway, so it's not necessary. Like it doesn't bias. Like rflag doesn't have any argument saying what is the current value. So it's we can do that, but we don't need to. Like it's just giving you ownership to read everything. It doesn't tell you what the value is. So It's not useful. So now we start all the threads with rfrag1 by 3. We do speculative execution as before, and instead of signaling the first thread, I have some concurrent library called parallel commit system, PCS, and that has an invariant. So after starting all the threads, what main does is PCS.init initializes the library, and as a result, as a precondition, it transfers all the auths to that invariant. So they all live in the invariant of the parallel commit.
During the speculation phase, like for each of the transactions, do you know what slots are being hit, right? Like from all the pre and post states.
From all the
So like I guess like in like transaction 1, like beforehand, like you know what slots.
what accounts are being what accounts, we in this example we know we have a static analysis to figure that out. So so what happens is like the one difference is at this time before speculative execution you have to declare to tell the parallel commit system that what's my footprint. So DFP stands for declare footprint. So we have to declare, every transaction has to declare its footprint. It can be a set of states, it can be all the accounts. So before speculative execution, we declare the footprints. And now let's say, as before, the second thread finishes first. There is no need for us to wait for AC1. Like the transaction, the parallel commit system knows that no previous transaction writes to TB, to AC2. So it immediately wakes up the second thread and it takes out from the invariant RR2. Sorry, this should be RR2. Takes out RR2 from the invariant and gives it wakes up the flag and then it can merge right away. Doesn't need to wait for the first for TA to finish. And then it calls done, and that then puts this back to the invariant. But now it has the new state like PB2 up and apply the transaction TB to it. Okay, so now let's say TA finishes and now it calls wait, and now it takes that part out from the invariant. And now let's say at the same time, while TA is merging, TC also finishes. And then TC can concurrently take out even that part from the invariant. And then TC can say do the merge. Now it has the new state, it calls done. And then the second part, like the RR2 moves back to the invariant. And then concurrently, TA does the merge. Then it updates the RR1, and then it does the done, it goes back to the invariant. Then finally, we have this PBS wait for all. And then the post condition of that takes out everything out from the invariant. And then we do a little bit of equational reasoning to say that these are both apply all the transaction. But that's fine because TC and TB don't even touch PB AC1. So these equations work out. And then we can combine the two ROs to one ROth. And then that was the post condition of execute block as before. So one thing to note here is that where it has, so TC retry is less likely here. Why? Because we didn't wait for, previously we merged here, like after the first transaction merged, now we merge right away. So that makes it's less likely that TC saw a stale value. So less likely for TC to retry. And even if a retry happens, it will happen in parallel here, right? It will happen in parallel with here. It's not waiting for R1 to TA to finish before doing the retry.
So if you have like, let's say like, instead of like 3 transactions, you just have like three components that like transactions with them, where like component 1, they all kind of touch the same state, component 2, they all kind of touch the same state, component 3, they all touch the same state. Would the same strategy work? Really?
Like each component is a set of transactions?
Right.
Yeah, okay.
Yeah.
It will work the same way. But this is actually implemented, and I've only tested it on like the first 1,000, first 1 or 2 million blocks, and it had like 3-5% speed up. Like it may have more speed up in the later blocks, which have many more transactions. then there may be like long chains, and so I haven't tested it yet. That was all. So yeah, questions.
Yeah, I guess this is like semi-related, but like, I guess like contested state, do you think that's like kind of a good proxy for like the number of retries that you'd have? Like, yeah, I guess like what would be like a good, what would be like a good proxy for like the number of retries? Either like the original, like sequentially emerging or like the parallel emerging.
You're saying like how can we predict like how many retries would happen? Like can we somehow predict?
Yeah, is there
Okay.
like a way that we can predict like retries?
I see. So one is like my static analysis computes the footprints, so we can see the overlap in footprints. That's one way, and then I think in the execution team, I think we are doing something where we use the historical data to predict. Yeah, we can do even a mix of both. The static analysis, like there is room to make it faster, and there's room to make it more more like more powerful in predicting like the most tight bounds on which accounts it would change.
Sorry, you're working on this proof comment for the.
No, I'm not. It's just like just it was just an example to show like other ways to split. There are many more ways to split. So maybe while we're waiting for questions, like I think there's one more piece left for concurrency. So we have this scene, and that's already gets us a long way by concurrent invariance. There's one more piece called ghost locations, where like these are like physical locations, but we can store like arbitrary mathematical data in those locations, and we can split their ownership in completely arbitrary way. Like Iris has a concept called a resource algebra. It specifies that an algebra must have these operations and satisfy these properties. And once you can come up with those, you can define very fancy and very powerful ways to split the ownership. You can say like there's one thread that can only increment the counter. We didn't see anything like that here. Like we said that one thread can only change, but we didn't say like it can change only in this way.